different types of capillarity, forces, and so on in colloidal science. Now, I won't let you go off that easily, however. But before we begin, let's just get reminded. We have these nice pictures, but what's hidden behind this picture? How can we use them in different types of devices, in high technology, in manipulation of colloidal systems, and so on? So you tell me that. I suggest that we follow more or less this scheme, but it's really up to you. Before that, however, we had one problem which we didn't solve during the lectures. So I'm announcing again the Fast Response Award. If you remember, we had this problem. This is kind of the wake-up problems. Hopefully this will energize you for the discussions. Now we have a cylinder. And we start eventually dropping more and more liquid on the top of the cylinder. The amount of liquid increases. The liquid approaches this contact. It's not a contact line, just the periphery of the cylinder. Now what is the condition for the liquid flowing from the top of the cylinder around on the walls? You have seen this phenomenon for sure. It's important in some technological processes. But how do you define the thermodynamic condition for the overflowing liquid? It takes some time to figure out. Once you figure out, you'll be like, gee, I mean, that's all simple. So it's nothing complex. Think about something simple. I see that Ketan there is making right movements.
Contact angle goes to 180.
Sorry?
Contact angle becomes 180 degrees.
180?
90 or 180.
No, the contact angle is a thermodynamic parameter. You can't change the contact angle. You can think analyzing what was going to happen. So the liquid increases in volume, then it's going to reach this point.
But does not the contact angle change on the surface or on the periphery? If you are on the edge of the cylinder, won't it have like a tendency to stay together still some more?
No, the contact angle for a liquid and solid is constant. So you can define something through the contact angle. I mean, this is a good approach, but then exactly what should happen for the liquid to overflow?
The weight of the liquid that's going to pop out on the sides should be balanced by the surface tension force.
Right. But I mean, like you can even consider the liquid to be, weightless or to have small weight. I mean, the liquid can still even protrude a little bit out of the surface. Actually, it's going to do that. But then, at what point is going to start overflowing? So the weight is not that important. It's the weight is not the thermodynamical condition which determines the overflow.
Does it have something to do with the internal pressure?
No, not really. I mean, like the only thing that you need here is the contact angle.
Is it when you can no longer minimize the surface area of the drop anymore?
By increasing.
Well, what you're telling me is when thermodynamically the liquid should overflow, which is right. But I mean, when exactly does this happen? In what moment of the droplet enlarging and expanding and eventually expanding outside of the periphery even of the cylinder? At what moment is it going to happen?
What about when the contact angle goes beyond the advancing contact angle of the vertical surface now?
In this case, I mean, you're on the right track, but don't even think about advancing or receding contact angle. Think in terms of only thermodynamic contact angle. Assume the thermodynamic contact angle is the advancing contact angle. So what is the condition for the overflowing here? I think this is a problem which will make you remember the contact angle for a long time and understand how it works in many cases. So it's very simple. What will happen when the volume of the liquid expands further out? At what point the liquid will start moving in the other direction? It's simple. I mean, the answer is very simple. Chris is willing to.
Is that something to do with the fact that it has to stay spherical? And then when this contact angle gets past the contact angle with this side right here.
Okay, I see you're on the right track, so you win the kind of the fastest thinking award today. So the answer is very simple. When you enlarge the droplet, so this essentially hanging meniscus here becomes essentially meets this surface at the contact angle, then the liquid is going to start overflowing. Which essentially is just another expression of something that we already know, and that is that the liquid is going to move on top of a solid surface only when it meets the contact angle, or is the angle at which the liquid meets the surface is a little bit bigger than the contact angle. So the moment that the hanging droplet approaches the contact angle on a solid surface, it's going to start moving and the liquid is going to overflow.
But what is the condition for the liquid to move around the corner?
Well, the liquid, first of all, if you have gravity, it would like to minimize itself downwards. Even if you don't have gravity, you're going to have an ideally spherical droplet. But this droplet would still at some point would like to start moving, kind of engulfing this body when you increase the volume of the liquid. And the moment it's going to start moving, either because of gravity or because you're increasing the volume, is going to be the moment when the surface of the liquid meets the surface of the solid at the contact angle of the liquid. Okay, I think I have talked enough for now. Now our first speaker will be Tiffany then. And she's going to tell us about, you can use this mic if you like, or if you like the movable one. You're going to use the camera, right?
Yes.
Chico, can you switch the camera so that it's on top?
Yeah, okay, great.
That's good.
And maybe we want to zoom out a little bit. Can you zoom out? Can you zoom out a little bit? Great. Okay. You're on.
Okay, good afternoon, everyone. My name is Tiffany Bailey. I'm a graduate student in the chemistry department here at NC State. And my discussion topic will be today, driving of droplets by surface tension gradients. Now, this discussion was based on a major paper by Chaudhry and Whitesides called How to Make Water Move Uphill. And we'll start with a question. Does anybody know how does the droplet move uphill against gravity? Any suggestions, questions?
I mean, like that should be from the.
Okay. Well, basically, we're going to start by speaking about contact angles. And Dr. Velev, he went over this, so this may go into a little more detail. See? In this diagram here, it shows a contact angle at A and a contact angle at B. Now, as you can see, the contact angle at A is smaller than the one at contact angle B. And it tends to shift. And here's a water droplet on a surface gradient. That's important to know. So what happens is the water droplet tends to shift towards the highest surface free energy for the solid vapor phase. And this is shown in this diagram here, actually shifts towards the higher energy area. So what happens when that happens, it decreases the area of the vapor-solid interface while increasing the lower free energy. It also increases the total area of the solid-liquid interface. And these are the principles for how the actual water droplet moves. Now that we discussed the contact angle, we'll talk about the gradient effects. Now, in the Whitesides paper, they actually took, it's called N-decyl trichlorosilane, mixed in with a mineral oil, and they actually vaporized it on a silicone wafer. And when this happens, you have one side of the silicone wafer, it shows properties of being hydrophobic. Then on the other side, it shows properties of being hydrophilic. So as you can see, the angle decreases from hydrophobic to hydrophilic. And those are the effects on the angle for the gradient. So how does the droplet look when it moves? As you can see here, within the Whitesides paper, the droplet actually moved about 1 millimeter per second. And it was on a 15-degree inclined plane. And here's a picture of that now.
Can you zoom in a little bit on the picture?
Okay. There have been several studies on how to increase the velocity and to increase the movement of the droplets, but I'll just focus on the horizontal form right now. But there's also people are trying it radially, with a circle, with a sphere. The next question would be, where could this application be applied in the industry? Anybody have any suggestions? Dealing with water droplet movement. Why would we need that?
Heat exchangers would be good, I think.
Okay, heat exchangers. Anybody else?
Car seal.
Okay. Well, several microfluidic devices could be used. We also have microchips equipped with microfabricated miniature fuel cells. We also have power sources in laptop computers, military uniforms with coolants, and other portable devices. Now, one part of the discussion that I'd like to talk about, something that has been going on with a lot of research, is the difference in the velocities. There have been like a discrepancy between several authors about what actually is going on with the velocity. Now, in a paper with Daniel and Chaudhry, they reported that the velocity of a drop was proportional to the radius of the drop, but it became 0 at the finite value of the radius. However, in a paper in 2000 from the Journal of American Chemical Society, Lee and Abness reported the velocity was proportional to the unbalanced Young force, or the hydrodynamic force explained by conventional interpretation. The latest paper that was produced was in JACS on November 2002, where they're disputing both of the previous papers, and they feel that a slight change in force causes a big change in the velocity. And they presented experimental results that can be explained by their new friction theory. So these are topics that I wish to explore more when we get into the paper.
Well, questions from the audience? Now, first I have a few questions, but you have the floor first.
Okay.
I thought that the drop would want to spread to a surface of lower free energy and not higher free energy.
Okay.
That would be the one that it would want to preferentially wet more.
Well, it would, but we're dealing with the surface gradient, so it wants to move towards the hydrophobic end. No, the hydrophilic end. I'm sorry.
The hydrophilic in this sense really will be higher. energy.
Surfacing.
Okay. Maybe I'm mistaken.
Hydrophobic is oil surface. And,
Oh, yeah.
If you just think about
Fluorine,
energy,
fluorine.
which interfacial tension is higher, water or oil?
Water. Okay.
So that would be quite higher energy.
Okay.
Now you make these things yourself, right? To Jan Genzer and with Chris Gorman.
Yes.
Now what technique do you use to make that?
To make the
To
gradient?
make the gradients, yeah. Do
Um,
you use vapor phase or?
We use a vapor phase. Like I said, I've actually tried this experiment before. And like I said, you take N-decyl trichlorosilane, you oxidize the silicon wafer.
You can draw some
Okay.
just on the sheet there.
Okay.
Here, what how the chemistry works.
Okay. So basically, I can kind of draw like a model of how it looks, okay? We have these boats actually tailor-made. So what we do, we put what we actually want to be vaporized on the silicone wafer in it looks like a little tray. So then it actually, you leave it on for 5 minutes and it actually vaporizes onto the silicone wafer. So once it does that, after 5 minutes, you can actually tilt the silicone wafer, maybe 15 degrees, and you place, I say about 1 microliter drop there, and then it actually moves upward. And
So
that's, yes.
Is the vapor deposition diffusion controlled? So that's why it's
Harder to
you get a
penetrate.
gradient because
Right.
some parts it just goes right down here and then it has to travel.
Right. So this would be the hydrophilic part here, and this is the hydrophobic.
Okay.
So once you put the droplet on, it wants to go towards the hydrophilic part.
What is the high speed that you can obtain?
Well, in the white size paper, it only moved 1 milliliter, 1 millimeter per second. But I don't know. I've seen it move a little faster. So that was the first experimentation that was published. So now they're actually doing certain experiments with, they're dealing with coalescence and making it move really fast with steam and all kinds of things. My project now, I'm actually looking at what actually can move along the surface, which viscosities and different things can actually move across the gradient.
Can you move organic oil?
It's about that.
Like silicone oil or carbohydrates?
I don't think so. I mean, I haven't tried. I've tried glycols, but I don't think so.
The
It's
water
so
moves
heavy.
in that direction,
Oh,
maybe
yeah.
this one will move in the other
Right,
direction.
right. So,
Okay, questions? Chris, yes, no?
So
yes.
if you had
Speak louder.
if the droplet was too big, it probably wouldn't go up because it has to fight gravity and because of its own mass, or it'd fall apart.
Well, that's
If it-
something it probably won't, but that's something that people are looking at now, like exactly how
So-
dense. Or,
What I was going to say was that if you get it smaller, it obviously goes up. It's able to go up faster and faster.
Right.
Is there a maximum?
I'm not
By
sure. about
radius?
But see, the thing is, though, is that the bigger the drop, the farther the drop reaches, and so you're going to have an even greater disparity in the contact angle, and so that might cancel itself out.
It still has to fight gravity, though.
Yeah. But, okay.
If the one Chaudhry paper is like 15 degrees, so there was no gravitational effects in that.
I guess there's a point where it'll fall.
So you can find arguments for and against. I mean, essentially, the larger droplet moving faster or slower or stopping. That's interesting. I don't know the answer
Right,
to that.
I'm not sure.
Maybe nobody does. Daniel.
Do they know of any of these occurring naturally in nature?
That's an interesting question. Whether this can occur naturally in nature.
Not that,
Not that you know of.
not that I know off right hand, but it might.
I was wondering if you've read anything about that.
I haven't read anything about that.
Well, we want to give the floor to everyone. So maybe actually Shane will try to answer that question when he comes and tells us about other methods for making droplets. So.
We'll
Okay.
pretend that's true.
So, if something occurs naturally, does it happen anywhere else in nature?
things. You should show this actually to us sometime, or maybe people who are interested can come in your lab and see how the droplet actually moves upward. Which one is yours?
Yeah, right there.
Okay.
All right, good evening, everyone. Those of you who don't know me, my name is Shane, and I'm following up on Tiffany's presentation, unintentionally, actually. All right, first I'm going to go over the Marangoni effect. I didn't know about this until recently myself. It's also called the tear of wine effect. If any of you drink wine, you'll notice your wine glass will have, it really does, it looks like a tear coming down the wine glass. And that's just from, at the meniscus, you get a preferential evaporation of one substance over the other, and it crawls up the side of the wine glass, and then it comes back down as you drop. And that's simply the Marangoni effect. Now, this is a little different than what drives the droplets up a gradient. Motion of water up an incline. This is actually driven by different forces on either side of the droplet. The driving force is surface chemical potential gradient. This can be set up by deposition of a chemical, like Tiffany said. It can be some alkyl trichlorosilane if you're trying to get water up a hill, or there's other ways of doing that. And this comes about from an unbalanced Young's force. I've written the equation out for this force, and Chaudhry and Whiteside seem to stress the surface vapor gradient, but it looks like it's more of the differential between the surface vapor and the surface liquid that has a lot to play with it than just the surface vapor alone. For this one, as you've already seen, there's a 15-degree slope, and a couple milliliters went up, or microliters went up at about a millimeter per second. And here's a diagram of the receding versus advancing contact angles. And increasing cosine theta means increase in the delta gamma, of course, from Young's equation. And that's all I'm showing here is the difference between the
So the driving force is actually the difference between the two angles, right?
Yeah.
You can consider this difference here.
Right. And
As
since
its driving force, it more or less stays constant to what I see.
and pretty much the liquid vapor energy stays the same, so that's basically a constant throughout this. And photoresponsive surface. This is a paper by, I don't want to mess up their name, Ichimura and Nakagawa.
Yeah. Oh, yeah.
So if I screwed up their name, I apologize to them. And they use different lights to actually activate isomers on an azobenzene that was on the surface. And they noticed a difference between the UV and visible blue light on which isomer was produced, and this created different gradients going up the hill. This was completely thermodynamically reversible. This is very important if you want the gradient to go both ways. You've got a switch now. Add in the like an OTS or DTS to the surface is irreversible. Right here, we've just, like I said, we've just added a switch to the system. We can now control this. And different isomers have different degrees of phobicity. I gotta quit doing that.
You can put it in your pocket, actually.
I'm gonna do something with it. All right. And here's the other paper I believe Tiffany was referring to. This one had to do with nucleation growth of water in the presence of saturated steam. Now, they actually compared it to if there was no saturated steam present, and they noticed a couple orders of magnitude increase in the velocity of this. And now, it was pretty neat how they created their gradients here. They actually took those of you who do contact angle measurements, I'm assuming they used a syringe like that, and actually put a drop a couple millimeters above the surface and let the gradient grow radially outward. And then they exposed this to saturated steam. Now, they kind of hypothesized a couple different reasons of why this is happening, but I got the notion that they don't really understand it either. Well, they wondered whether or not it was, well, they even said that. They weren't trying to hide it. they were wondering whether or not it was due to maybe wetting of the surface and adds like a lubrication effect. Remember, the zero slip condition fails in a system like that. Some of you have taken fluid dynamics before. It fails in a system like this. So it could have been wetting of the surface, and they tried to explain some different reasons, but they really didn't quite know why it was. I'm sure it has a lot to do with the fact that saturated steam is going to drop the liquid vapor interfacial energy pretty markedly. And for their gradient, they used some alkyl trichlorosilane again, and I think they switched from 8 to 14 carbons in there. And again, about 2 orders of magnitude greater with the saturated steam. Now here, there's one paper that I've seen. There's a few out there now, but they used electrochemical means to drive this. And this is something else that it goes in one direction from, I believe, it's the cathode to the anode. So, I mean, switch the cathode and the anode, and again, you have a switch. You switch your gradients. And here's a diagram of dewetting of an aqueous film on a microscope slide, and electrodes treated with gold. And this is just water dewetting of water. And here's a slide from Dr. Genzer. I use this with permission under the, he wanted me to leave it as is, so that's why it's looking like this. That was his specifics to me using it. But Jim Semler, a graduate student who's about ready to finish up at chemical engineering, created droplet movement of PDMS, which those of you who know anything about polymers, PDMS has a glass. I mean, you're never going to see the glass in PDMS. So it's a liquid, and he drove it across a glass slide using a thermal gradient. Now this also is, I mean, this is reversible. Here's your switch again. And the bottom figures, he put glass on top of, I guess it's graphite, like for a pencil, and put electricity across them and heated it up to 150 degrees, and they controlled intervals of which they're pushing the PDMS across the glass slide. So it's another way of creating a gradient purely by temperature. And that's the end of my presentation. Does anyone have any questions?
I hope so.
I thought the radial spreading of the drops, the reason that they were able to get such fast speeds was actually coalescence, because they were measuring it by the center of the drop. And as the drops ran away from the center, they would merge together. And
They think.
I actually thought that was sort of cheating, because the drops were going to be these huge drops, but they were measuring from the center, and that was growing even faster away from where they originally.
They also didn't scale their diagram. You have absolutely no clue what size. They didn't put a scale bar on that diagram.
There is a bit of vague claim there that actually in this case the surface tension gradients on the surface acted also on the same direction as the surface tension gradients because of the heat, essentially the heat gradient. So the heat gradient, which is the Marangoni effect in this case, like the first slide Shane showed, actually works in the same direction as the interfacial gradient on the substrate. But that was a little bit unclear. Just to complete what Shane told us, now there is one more method for moving droplets by using contact angle. And actually Manoj Chodkuri, who visited the department a couple of years ago, less than a couple of years actually, showed this method. Yeah. So you can just mechanically move droplets by, let's say you have a surface now. If you jerk it fast, just because of the inertia, the droplet is going to stay in place. If you move it slow, it's going to move together with the surface. So if you start moving the surface with asymmetric motions, the droplet can move in principle in any direction without a gradient of the contact angle. So he had envisioned some microfluidic chips where the droplets move around just because of the surface jumps around. I think he had a paper published later about this one. Anyway, questions to Shane? Now, do you know anything that's related to modifying of the surface by using self-assembled monolayers? I think there were some papers like that. Creating a gradient by self-assembled monolayer rather than by chemical means.
Over my group, we actually built a machine where it's got a shutter inside the UV ozone. So we saturate the silicon with one monolayer, saturate it completely. and then you pull it over and it'll create a gradient by the UV ozone. It'll pull it off selectively. So you've got, I mean, absolute control over what type of gradient you have on
So
that.
you're using the mono layer as a mask or as a sensitive layer?
What do you mean?
Is it a mask which modifies what happens on the surface below?
Yeah,
Or-
we add like OTS.
Uh-huh.
We deposit it on there either with mineral oil or vapor
mm.
deposition, and then we pull it through. Because you get, whenever you use vapor deposition to put those gradients on there, you have some differences laterally. I mean, have you noticed that? Yeah, we have. It's hard to reproduce it too. So this way, it gives you a nice uniform gradient the entire way down, and we can fit curves, and you have complete control over how you get your gradient.
Huh, interesting.
So
Yeah. Uh-huh.
I don't run the equipment, our postdoc built it.
Okay. Questions? Chris had one or? Okay. Okay, let's move on to the next. Now, who would be the volunteer here? Okay, thanks, Shane.
Thank you.
Here is. You know what? If you're going to stay there, why don't you use this one? Sure.
All right, I'm Brian. I'm gonna take over after Shane. If I can find mine. And the reason I'm dressed so oddly is because I just came from an intramural basketball game where we got stomped. And I'm going to continue the talk on spreading and moving of liquids on surfaces. And generically speaking, when you take a droplet of water, as you see in the top, with a surface tension of 72 millinewtons per meter, and you add surfactant, as I've shown a little cutout on the bottom, it's essentially like putting this little oil phase, which is segregated only to the surface, lowers the surface tension, and it spreads because of what Shane was alluding to as the unbalance of the Young force. And so that equation, gamma equals gamma liquid vapor times cosine theta plus one of the other ones is no longer equal. So until they become equal, the drop will spread. And that's just for kind of surfactants in general. And what I'm going to be talking about today is actually these things called super spreading surfactants, which actually spread orders of magnitude more than just normal surfactants. So what you see here is a picture of a leaf. And on the top is a droplet of water. Right below it is this thing called Triton X100, which is just a generic surfactant. And the drop that you can't see actually, I can't find my mouse, but it actually takes up this whole area right here, the shiny part. So it is spread, almost 50 times more than the generic surfactant holding drop. And these molecules are called super spreaders because they spread so quickly that the droplet almost is spread and then evaporated. And so these were first discovered, and nobody knew how they worked about 30 years ago in farming, because you have these people who want to spray and deliver some medium to a plant, and they don't want it to beat up on the leaf and roll off. And so this just worked perfectly. And then, as you can see, both of this picture and this graph of surface tension versus log of concentration came from a product sheet for a company where you can buy this super spreader, which is called Silhouette L77. And these are sort of different than normal surfactants in that if you go back, I actually drew this incorrectly. Normally you have kind of a polar head group, as I've drawn, like a blue dot, and the hydrophobic, it's usually a hydrocarbon chain, sticks out into the air. These work differently. You have the hydrophobic head group, which actually sits on the top, and they have a long hydrophilic tail, which one of the best ones in industry tends to be when N equals 8. And what you can see is a pure water droplet having some area 1, and then regular surfactant, just non-ionic, would spread 2 or 3 times. And then with a trisiloxane surfactant, which is what these are called because they have 3 silicon groups in the hydrophobic head group, spreading about 50 times. And as I said before, nobody really knew why this happened. Why do they spread so well? And there are kind of 2 major theories right now, and they're in major competition. And what I did is I actually, you can get some of this stuff for free if you just email these people and say, I'd like to try this stuff and see what it looks like. And so in the right is a little vial of that Silhouette 77, which is just a mixture of different enantiomers of the trisiloxane surfactant. And it's about less than 1 weight %, and yet it's incredibly opaque and cloudy.
Chico, can you turn on this on the other TVs?
Yeah, actually, that would be great. Thanks. And on the left is just SDS, well above the CMC point, and yet still very, very clear, transparent. And so one of the hypotheses is that the reason that super spreaders work so well is because all of these little aggregations of surfactant in the droplet burst and flood the surface with these surfactant molecules, which just continue to spread the droplet across the surface until it's completely spread. The capillary forces are equal, and then the droplet just evaporates. And I found a paper by the guys at the bottom who say that no, this is not the case. What really happens is it's essentially a gradient in the surface tension forces that cause the droplet to spread. And so they did 2 tests. One, they took just a droplet of water, as you see on the left, and they gently dropped on the surface without breaking the surface tension of the drop an amount of this super spreading surfactant. And within 1 second, you see the drop just spread about 10 times its area. And then they did an experiment where they did the same thing, but they cleaned the needle tip, dried it, and removed any trace of surfactant from the external portion of the needle tip, and then injected it through the edge of the drop to the contact line on the solid and injected the surfactant, and then removed the needle very carefully. And nothing happened for about 2 minutes until diffusion took over and diffused the surfactant to the top of the drop, and then the drop spread. So they've kind of cleared up this region of unknown, whether it was the turbidity that caused the surfactant, the drop to spread, or something directly to do with the surface of the drop.
Hey, I'm sorry to interrupt, but can you talk a little bit louder?
Oh,
maybe he can move the microphone a little bit later.
Okay.
Up towards your bottom of the field, because it's a direction. Sorry about that.
No problem.
I barely hear you.
Okay.
Well, while he's doing that, I can mention that this guy is actually my master thesis advisor. So
Nikolov.
yeah,
Okay, so
good experimentalist.
So I thought that that was just a very, very cute experiment that got right to the point and pretty much demonstrated that turbidity does not cause this incredible spreading of the droplet. So these guys say that, again, it's the Marangoni effect which is causing the spreading of the droplet. And what happens is that there's actually a gradient of surface tension all throughout the drop, where if you think of the drop as the top of it being this one big surface over which you have to spread all these surfactant molecules, there's one point where there will be no surfactant molecules, and that's the contact line. And so it's going to have the highest surface tension anywhere in the droplet. And it's also going to have the lowest surface concentration, as you can see in the inequalities below the little schematic I have. And so what happens is the higher surface tension wants to round the drop and pull it together, so it keeps pulling it out. And this happens, this gradient pulls the drop and keeps spreading it until capillary forces are balanced, and then the droplet just evaporates. So it spreads towards higher surface tension. Or you can think of it as it spreads where there are fewer molecules, which is out on the periphery of the droplet. And the way they traditionally do this is these drops are not round by any means, so you can model them as a little flat disk. And so the spreading rate, U sub r, is essentially equal roughly to this gradient in the surface tension of the drop, which is a radial gradient, and then the height of the drop thickness divided by 2 times the viscosity of the drop. And then because it's a disk, you can approximate it as this flat disk, which is the height would then be the volume divided by this ever-increasing pi r squared. But you have to conserve the mass, so the volume of the drop. So r is going to change with time, but v is always the same. And the thing is nobody really has a really good idea how the surface tension gradient behaves. So what these guys have done is they've just said, well, let's approximate delta gamma as a linear constant with time. And they just called it K. And as you can see, this is for two different sets of experiments, solid dots and open dots. And then the little dotted line is actually the curve R of t equals R naught to the fourth plus everything else, all to the 1/4 power. So they're just modeling how the radius of the drop spreads and changes with time. And I should say that the hollow dot experiment is actually a de-wetting experiment where they put the droplet of water onto a thin film of Decollin, and the droplet spread and pushed the Decollin away. It's just a high carbon liquid. And so it fits the exact same profile. And I found this paper by Degens to be really helpful for just sort of generic explanations. It's about 50 pages long, but it deals with just about everything in every kind of wetting phenomena. And I actually just printed out the table of contents in section 4-2, which is like the last 5 pages. The two papers by Nikolov are the ones that basically proved that it's not turbidity, it's a surface tension gradient. The paper by Hill is a paper where they use the disk model, but they're also the guys who are big proponents of the turbidity being the spreading cause. And I think they're kind of doing a little bit of infighting between each other right now. But as you can see, the Degens paper is fairly old, but it captures the physics pretty well. But the other two papers are very recent, and this is a very hot area right now because superspreaders have been around for 30 years, but it's only just recently kind of been determined what's causing it. And there's still a lot of questions to be answered. And I'll open the floor now.
Yeah, from what I know, actually super spreaders are gaining importance these days because they're used in Africa and tropical jungle areas. Essentially, when you want to cover fast, let's say with insecticide or whatever, large areas, I mean, you want to use super spreaders because then you're going to have lots of substance being. Now, one thing before the questions. Now, one thing that you could tell here is your experience with super spreaders, actually, which was mixed from what I remember.
Yeah. If we go back, there's a reason that I actually have.
It would have been whoever is interested. You can show on exactly how it works. Eventually.
Yeah. One of the things that we were interested in was when you have particles in a drop of water, because the surface tension is so high, that drop doesn't spread, and the rate of evaporation tends to be the greatest at the periphery of the drop. And so it causes this gradient of flow in the drop towards the edge, and it drags the particles by viscous drag, and you get a ring of particles. And if you so desire that, that's wonderful. But if you desire a thin film of particles evenly spread all throughout, then you don't want that to occur. And one of the ways to alleviate that ring effect is to have the droplet spread so fast that the particles are essentially laid down because the film becomes so thin that evaporation is almost instantaneous. And your uniform dispersion of particles is randomly distributed, boom, right on the surface. And no ring can form because there's no pushing of the particles to the side of the drop. So, because in relation to my project, I'm trying to take particles from liquids and throw them onto a surface and hopefully have some manner of control over that.
There were some droplets which are really, you drop them on the bottom of a Petri dish and you can see it like expanding and eventually covering everything around.
And I should also mention that
not always though.
These are ideal for things which are hydrophobic. Like you can get a droplet of water to spread 50 times normal what it would on polystyrene or waxy leaf surfaces. So I mean, it's less of an issue to get something to spread on a hydrophilic surface because you know it'll spread anyway. So that's what these surfactants are good for.
Okay. Now we should stop this dialogue with you and kind of.
We talked about the spreading of water.
Sure.
And you showed us the structure of the super spreader.
Uh-huh.
Now, I'm not thinking of the application, but if for an organic spreader, would this work? Like how we have mice?
Oh, if you.
I don't know.
That's a really good question. Do you think it would stick the chain outside and put the...
This looks like just the opposite because the hydrophilic part is longer here, right?
Yeah.
Is it? Yeah, it is. And so would a surfactant work as good for the organic liquid? Because that might help in lubrication or something like that. Just something that.
Well, that's a good question. I have to say that I've actually tried these on hydrophilic surfaces. They don't work very well because they want to have a hydrophobic surface to spread on. So the surface energy is not unbalanced enough. Daniel, did you have a try?
They use surfactants for lubrication of oil.
Yeah.
Not super spreaders though.
But it would be interesting to have something with inverted property. I think I'm taking too much time.
Well, anyway, in your practice, whenever you need to spread something, I mean, don't forget this new area, which helps quite a bit eventually.
Yeah.
Not always. As Brian finds. Okay. Now it will be good to continue right after super spreading, to continue with the exactly reverse case, which is super hydrophobic surfaces. So in a way, super unspreading. So Angelica is going to tell us about this. Eventually, colloidal science is like that. It's an old science, but these days you have high technology. So people would like to really expand the boundaries. So what they do is, first they try, if you have spreading, it should be super spreading. If you have non-wetting, then it should be super non-wetting. So Brian told us about super spreading. Angelica is going to tell us about super non-spreading.
Should probably save it to the desktop tomorrow.
Okay. Going to steal a picture that you have here. And is this one the?
This is called the synergistic effect.
Yeah. Just well, Brand was talking about how water can spread on this surface of the leaf, but if you see when there is no such a super spreader on, then the drop of water will remain on that surface. So you can see there that on leaves that are like so old that we can not even know when they appeared on Earth, they had these super hydrophobic properties, and there is an analogy between how these natural super hydrophobic surfaces and the super hydrophobic surfaces that we can make in like nowadays, right? Like, so one of the thing is.
Two more to the right. One more.
Sorry. Okay. So with that in your mind, with how this drop of water stays or remains on the surface of a leaf, what would the reason be for the drop to stay there and form like almost a perfect sphere on top of that leaf? What would you think about that? What would be the reason for this to happen? I don't know if I was clear enough. If you have this is the surface, and then let's say this is the leaf, you'll have something like this, and the contact between the drop and the surface is just very, very small. That means that this surface is really super hydrophobic and there is no spreading at all. So why would you think this happens in surfaces like leaves that we can find in nature?
Low contact area.
Flat.
It is because of the flatness and.
I would say it's because of the bumpiness.
So they're not.
Right.
That's what
Right. Okay. Yeah. This the reason is what you just said is because of the irregularities that are on the surface of the leaf that will cause that the water not to spread out on the surface. So there are several studies, and one of, like Shane said, like there is a high contact angle, and that's one of the characteristics of the ultra hydrophobic surface. And there is a low sliding angle, or the difference between the receding and the advancing angle or contact angle. So that means that if I could somehow create a surface with with such a roughness that that drop could not go or could not slide on that surface, then I will have a very or an ultra hydrophobic surface. So how can I do that? Well, I can create a rough structure on a hydrophobic surface with a contact angle which is higher than 90 degrees, or modify this rough surface with materials with low surface free energy. And what? One of these materials could be fluoroalkyl silane, and the reason is, well, this is a naturally hydrophobic material, so this could be one of the ways to do it. There is some other ways, and
is it actually used in making gradient surfaces or not? Fluorinated silanes, are they used in also making gradient surfaces or not? You just use alkyl silanes, not fluorinated silanes, right?
That's not
Uh-huh. You can get some ideas for research here.
I don't see why not. Why can't? Yes.
Maybe nobody did it yet, so Shane or Tiffany can have the chance of doing that first. So.
Actually, I've got a fluorosilane on record, but we never use it for gradients.
Anyway.
Okay, and one other thing that I was going to mention is that there are other surfaces that have been used as super hydrophobic surfaces, and these are fractal structure on these surfaces. A fractal structure is just a repeating structure in the same pattern like tons and tons of times. So with these fractal surfaces, they have found contact angles of 175 degrees, which is like very, very hydrophobic. Well, applications we can use in textiles, coatings, gene delivery, and microfluidic channels. So there is a lot of applications, or there are a lot of applications that include super ultra hydrophobic surfaces. One of the examples that I didn't put in here because I wasn't sure it was so formal. It is Dr. Ganser's super hydrophobic surface, and it's nothing but he took a piece of an elastomer and he extended it.
You can draw it in some way. It's not that easy to draw, but the people who don't know how this works should maybe. And it also uses, it's good in terms of the previous lecture from this class, because it uses self-assembled monolayer. But you can press the self-assembled monolayer.
Right, so you will have, let's say, that you have, this is like the regular surface, right? So you have a monolayer here, and once you stretch it, you can.
I'm sorry, Angelica. Can you move to the right a little bit? Perfect. Thanks.
Okay. So you can attach or put the monolayer once you stretched out this surface. So when it goes back to the original position, you'll have all these chains like very close to each other. And that's, if I have one very close to each other, then I will have like a very, very rough surface on this, and this will give me a contact angle like very, very big. And that's one thing that Dr. Ganser did in once. of your
So
experiment.
a good example would be those Docker Nice Pants commercials. The guy
States
Right,
defender.
right. That's
Yeah.
one of the textiles applications. It's just that.
Huh?
Have you seen that commercial? That
People without TV, what is that?
Man's wearing shorts and black
it
shoes.
just for,
One thing that you can try at home and actually works well is there is this hydrophobic agent for car windows, and I use this one and I'm amazed because sometimes you don't even need to use the wipers because the droplets are just carried away from the surface by the air. But if you think about gradients, the next thing would be car windows with gradients. So eventually the droplets would run away because of the interfacial tension.
right.
Must be fast
You can.
enough. Otherwise,
He's saying you're driving fast.
That's true, but you never know. About this compressed monolayer, essentially this release of the rubber is a way to make a super compressed monolayer. You cannot make this on the surface because it's going to collapse. However, if you put this on the surface of a silicone rubber and then let the rubber compress, you're going to beyond the compressed state, so it's kind of super compressed solid. If you remember from the phase diagram last time, when you compress a monolayer, you go gas, liquid, of course two-dimensional gas, two-dimensional liquid, and two-dimensional solid. What happens afterwards on a liquid surface is if you compress it further, it is really the equivalent of two plates going on top of each other, so it starts wrinkling and so on. It's the ones of you who have seen a big river freeze and then move. Has anybody seen that? I doubt this a little bit. I have seen this on the river Danube, but you can read it in Uncle Tom's Cabin or something like that. So you can see the pieces of ice actually moving on top of each other because they're compressed. This is what happens if you compress a monolayer on a liquid surface. However, if you put it on a solid surface, it cannot run away on top of each other, so it essentially gets super compressed, and then it gets to be super hydrophobic. That's how Young Genzer make these hydrophobic surfaces. Any questions, comments here, Daniel? Yeah.
I mean, what is it about the what do you call it? Dendritic, fractal structure on the leaf, other than the roughness? What is it? What's the?
Well,
why is it that this fractal-like that makes it hydrophobic?
it's the repeating of the structure what creates a highly rough surface. So that's the explanation they give. I mean, I don't know if there is something else that because it is fractal, then you'll have such a property. But it's because of the roughness, because it increases.
Yeah, if you remember the advancing contact angle, imagine that you have, let me see where I'm here, okay. Imagine that you have a solid surface, the advancing contact angle will be close to the receding one. Now if you start crumpling the surface, then the advancing contact angle would be equal to this angle rather than this angle. Now imagine then that you have a surface which looks like something like this. Then just the liquid moving on top of this surface is going to be very hard, and that makes the advancing angle really very, very large. It just cannot move through all those small thingies on the hydrophobic and hydrophobic and fractal surface.
Does the increase in surface area has to do anything with this? If you have a more rough surface, you'll have like more surface area of contact. Like instead of the higher advancing angle.
Not really in my view. The thing that has to has is essentially how it's very similar to what I started here. For the liquid to go, let's say, through the edge, it has to meet the contact angle. Now, if you make a very rough surface, then there always is going to be some edge where the liquid really has to go very, very high, at very, very high angle in order to start moving on that edge.
It's more that it cannot slide than it has more area.
for such a surface, the contact angle are reproducible.
Good question. It's so high anyway that it's difficult to measure.
Yeah.
Because they're measuring the macroscopic contact
Right.
angle,
Right.
not the microscopic.
So I think the contact angle is at some metastable state. It's not equilibrium state. So it's reproducible.
Right.
I doubt.
Okay, let's go in order of the question.
Let's say you put the drop down really with the, you force it down there, will the contact angle be basically anything you want it to be, or will it actually recede into the almost 180 degrees?
It would recede on top, so that's what you measure. Is that what you're asking? Like if you compress
Yeah.
liquid against the surface? No, because in that case, you have an extra tension acting on. So if you remember Young's equation, what you measure is the difference between these three surface tensions. So if you're compressing this, then you're adding a component here, so it won't be. I'm sorry. You have this, and this, which is vapor, solid, liquid vapor, and liquid solid. So it's the difference of this what gives you what this angle is. So if you're compressing this, then you will be adding an extra component for the summation of these forces. Remember that we did that, like.
But now actually the microscopic angle is very different from the one that we're actually seeing. That's where my point is.
Now this is a good point. In principle, the contact angle is thermodynamic parameter, so it cannot change by, let's say, pressure. At least not until you have very high pressure or something like that. Now, what you're telling, however, is important. This is important for those of you who are going to measure contact angle actually in practice. There is a difference between the macroscopic contact angle and the true contact angle on the surface. In a sense, what may happen is you may press it, and just because you have pressed the droplet and you have high curvature, it may appear that the contact angle changes, for example. The reality, however, is the droplet is always going to meet the surface at the equilibrium contact angle. The curvature that you may see macroscopically, however, may change, but it will be wrong to extrapolate this curvature and assume that this is the curvature at which the liquid meets the contact angle. And this is important in measuring. So that's why people, when measure contact angle, they have microscopes, special types of technique for extrapolation and so on. It's not that easy.
Building on the same question, if you like press it and it wets the surface, and if you remove the pressure, will it de-wet also on the hydrophobic surface?
It will de-wet,
and it will collect back.
It will de-wet until it reaches the receding contact angle.
Which is
so
at
the
the
wetting,
nanoscale.
The wetting is the difference between receding and advancing.
That's actually at the nanoscale, right? At that point, if you have fractal surface. So at that point, you really wouldn't see it.
That's a good question. I don't know what happens to that. Angelica, or I can give you references about people making fractal surfaces. I mean, it's really impressive just to take a polymer and to make it fractal. And just this changes the contact angle drastically. I can show you images like that next time.
If it's so rough, you could find a point where it would meet the minimum receding contact angle. Like it could be right next to it.
The same reason why it doesn't spread could also be why it doesn't collect back.
We have to finish and give the opportunity to the last speaker, but what I would like to mention here, this is like exactly an example of what would be nanoscale engineering. So you just not only make a polymer surface, but by just controlling the features on this surface, you control the contact angle. And that's where colloidal science is going. So this day it's not only measuring, making a gradient, making it fractal, making it controllable, patterning, and so on. Anyway, there is one more cool talk here, which you have to hear. So. Okay.
I don't know. Maybe
the color is not black enough.
It's a bit bright, but it's fine. I mean, we can't do too much.
It's okay, we see it.
Okay.
Yeah.
Okay. Today, good evening. And today, my topic will be assembling of nanostructure and electrical micro devices via capillary forces. This slide shows what's capillary forces. We already learned the details in the lecture, so I won't go to the detail, but I want to mention that capillary forces are interaction between particles which is mediated by fluid interfaces. They are important for the self-assembling of macroscopic and microscopic particles, and even for the protein molecules and viruses. Also, I want to point out for the different shape of the surface, and they will cause the different type of capillary forces, like repulsive, attractive, and then we can also adjust the strength of the capillary forces. This slide shows the self-assembly of particles and the action of capillary forces. There are five small pictures. Picture A shows the main driving force in the conventional assembling process, which is the capillary forces make the particles come to each other, and there's another forces which is hydrodynamic forces. Okay. And the picture B shows the ordering of particles on the patterned solid surface. You can see they are different areas in the solid surface, and people can design the pattern that they want it, and then they get the structure they want. And the picture C shows the close-packed mono and multiplayer of particles. And D shows the small particles clusters, and D shows the regular arrays of particles with desired lattice shape and separation. So basically, people design the pattern and use and adjust the capillary forces and get the structure they want. From the literature, I find this is interesting for us to think. They try to compare the capillary forces and the chemical bond, and there are some analogy and difference for these two forces. Both of the forces are reversible at some level of agitation or temperature, and they are both of them interact through overlap. For the capillary interaction, the overlap happened for the many sign.
Yeah.
Okay. And for the chemical bond, the overlap happened for optical. I think we all know about this, and both of them are directional. But there are some fundamental difference for the capillary forces and the chemical bonds. Capillary forces are described by classical mechanics, but chemical bonds require the quantum mechanics, which is very different. And the capillary and chemical bonds are described by potential curves with different forms. And let's go to the thermodynamic details. And the capillary forces can act over distance up to a millimeter, which is huge. I mean, compared to the chemical bond, they only act over distance less than 1 nanometer. People think about this self-assembling first for the nanostructures, and first they want to follow some idea from molecular self-assembly, which occurs in nature, and which is I don't want to say it. Okay, they the molecular self-assembling is the spontaneous association of molecules, and it's successful for the generation of large structure molecule aggregate, and it involves the interfacial interaction and shape selection. I mean, we can think about like DNA, RNA proteins. You know, there's a lot of examples for the molecular self-assembling. So there's two concepts which is important for the approach to direct the assembling process, especially for the millimeter scales component. That's for the micro devices. So first, it's shape recognition. They must have the ability to recognize the shape, so they can they can get the special structures, and also the minimization of liquid-liquid interfacial free energy. That's because they want to use the capillary forces to achieve the structures. For the technique available to make the electrical devices, people normally use the photolithography, which is the principal technique used to make the microstructures for the electrical devices. But this technique has certain limitation. First, it cannot easily form non-planar or three-dimensional structures. As we know, they use the, I don't know how to say, is light, reproduce the pattern. Right. So it's just the plate structure. Also, it generates structure that are metastable, and it can be used only for a limited set of materials, which is like only sensitive to the light or some chemical gas. Now I want to give some example for the assembling of component larger than molecules. I mean, microelectrical and microelectrical mechanical system, sensor, microanalytical and microsynthetical devices, and hopefully we maybe solve the problem by the new technique. This is some result come from literature, and people do the study, and they find the capillary bond can be strong enough to hold the millimeter scale object together against the substantial agitation of the supporting fluid phase. That means they can get the, they can get the, how to say, stable structure. Also, they find that they can adjust the selectivity among different type of capillary bonds. They can tailor the shape of the interacting mini-site. Like I have mentioned in the first slide, they can change the shape of the uniform hydrophobic edge. They can pattern the distribution of vertical hydrophobic strips on the edge, and varying the density of the block in some edge. Also, they can pattern in the hydrophobic area on the face to be chiral, which is a different shape. I'm not going to more details, but I want to show you some very beautiful pictures. This is for two-dimensional assembling. I believe we already see it in the lectures, but this is some different structures. So they give.
So what you see here essentially are, let's say the black is hydrophobic, the other one is hydrophilic, and they would attract each other by capillary forces. So all you do, you make these small objects, put them in liquid or put them in a flask, shake them up, and because the capillary forces play the role of directional interactions, they self-assemble into a variety of cool structures, which may be electrical circuits, for example.
Yeah, I think they prefer attraction between the particles.
Right. This is 2D, and then this is a three-dimensional structure.
There's a three-dimension assembling. I like this very much.
This is essentially a three-dimensional circuit. Then you make connections, and when you turn the electricity, it goes through all the cubes, and then there are white emitting diodes inside which start glowing, just showing that you have assembled a three-dimensional circuit. And the way you assemble this circuit is you put the parts, which are these small thingies here, into a flask with liquid, and then shake them up, and then they self-assemble into electrical circuits. Huh? What kind of particle you use? This is PDMS, rubber polymer, and then here you have the hydrophobic parts are actually metallic parts. So it's a bit complex to make those elements. So this is not really something that you're going to do in the lab tomorrow, but you can just shake those things and assemble. So in principle, maybe you can design circuits like that.
Do they always assemble to form the same shape? I mean, if it's like a free energy curve.
Good question. If you put too many, then they'll probably form. They would always self-assemble in the same configuration, like molecules. They would always form the same crystal. Okay, that's not a question.
Yeah, I think we can think about it. It's a molecule, like we do the experiment. We want to make the molecules do reaction, but the force is not a chemical bond anymore. It's capillary force, but the capillary force is strong enough to keep the structure stable, but it's not as strong as the chemical bond because you do not need to make the reverse reaction to make it broken. So you might have some other way to do it.
Okay, final slide and to start.
Final slide.
Up,
yeah, I find also read several other interesting literature, but I'm not going to give the details. The title is The Fabrication of Cylindrical Disparate Bipartite Assembling and Forming Electrical Network in 3-dimensional by Self-Assembling and Biomimetic Self-Assembling of a Function as Symmetric Electrical Device. I mean, this literature shows what they can do. Like they form the network. I mean, they make some small circuit. And another important and interesting concept is biomimetic. That means they borrow the idea from the biologic, how the amino acid to form the structure protein, and each protein molecule form the higher level aggregation like beta sheet. So, but anyway, as a conclusion, I want you to know the concept of the assembling is applicable for the assembling of electrical micro devices. But there's some limitation, like it's not practical right now, and there's defect. People even don't know how to measure the defect or how to decrease the defect, and the fabrication is not able to do right now. It just belong to the study region. So.
But it's cool. Okay, we have to formally finish the lecture. Thanks, and whoever is interested can come and take a look here. So thanks. We can finish now. Thanks for all the participants. When it comes to, we're going to go back to these areas a little bit further on when we come to micromechanical system, when we come back to photonic crystals and so on. So we have the opportunity to discuss them in a bit more detail a bit later.
It's an interesting topic.
Yeah, I mean,
I do not have time to read more paper,
It's more cool than actually practical right now, but it's very interesting. I mean, you just shake things and then self-assemble into.
Yeah.
So essentially, you apply the concept of chemical bonds to colloidal materials.
Yeah, it's hard to do. I mean, for the real.